And I'll try this one more time. I'm going to figure out what the log base 5 of 625 is. And first I want to set that equal to x, and then I'm going to change it. 5 raised to the x equals 625. So 5 to the x equals 625. And a factor tree of 625 would give me 25 times 25, and that's 5 times 5. What I'm trying to do is get the same base here. So I have 5 to the x is equal to 5 to the 1, 2, 3, 4th power. Now when I have an equation and the bases are the same, that would automatically mean that the exponents have to be the same as well. So x is 4, which means the log base 5 of 625 is equal to 4. Now let's do the last one. First thing I want to do is set that equal to x, and then 6 to the x is equal to 36. 6 to the x equals 36. Now 36 is 6 squared. So 6 to the x is equal to 6 squared. Bases are the same, so therefore the exponents are going to be the same too. So log base 6 of 36 is equal to 2. And watch, I can do it again, the curly Q thing. 6 to the second is 36, and yeah, that's true. Let's move on. Okay, with these, again, I want to set it equal to x, even though it's not going to tell me, directions won't tell me to set it equal to x. Now I have 7 to the x equals 1. Well, I'm not going to be able to get a base the same here unless I think of it like this. 7 to the what equals 1? And that's going to be 7 to the 0. So x is equal to 0. Let's try this one. If I set that equal to x, 9 to the x equals 1. 9 to the x equals 1. Well, the only time I can ever get 9 to the anything to equal 1 is if x is 0, because any number raised to the 0 will always give me 1. One more down here. I'll set that equal to x. So 10 to the x equals 1. Well, that would have to be this. 10 to the x is equal to 10 to the 0. So x is equal to 0. So the log base 10 of 1 is 0. And this leads to this. It doesn't matter what your base is. Your base can be anything. It can be 9, it can be 8, it can be 73, but the log of any base of 1 is going to be 0, and that's because any base raised to the 0 is equal to 1. Isn't that cool? Now let's try simplifying a couple more. You see how these are a little bit similar too? I've got a base 3, and a 3, a base 8, and an 8, a base pi, and pi. I'm going to set them equal to x again, and use the curly Q law, which really isn't a law, but it works pretty cool. 3 to the x equals 3. Well, if you're trying to figure out what x is equal to, the bases are the same. If I just have 3, I automatically have an exponent of 1. So x is equal to 1. So 3, base 3 of 3 is equal to 1. Can do the same thing here. Set that equal to x. 8 to the x is equal to 8. So I did this. 8 to the x equals 8. And the only thing that's going to make this work is if that exponent is 1. So x equals 1. Same thing here. If I set that equal to x, now I know this looks weird because I have pi and I have a variable x, but that's okay. Just go with me here for a minute. Pi to the x equals pi. Pi to the x, pi is just a number. It is irrational, but it's just a number, is equal to pi. And any number can be written as that number raised to the first, so x must be equal to 1. Which brings us to this. It doesn't matter what your base is, but if these two numbers are exactly the same, it always has to equal 1, because b to the 1 is equal to b. They mean exactly the same thing. A few more examples. Let's set this equal to x. Now, here's the thing. This is called a common log. If it just says log log and there's nothing here at all, no base, that doesn't mean that the base was forgotten, that somebody messed up. What it means is that the base is equal to 10. That's what a common log is. The base is 10. And that 10 isn't going to be written. You just need to know that if there's no base, it's a 10, it's a common log. Now I'm going to rewrite this. 10 to the x equals 100. Remember that whole thing a while back about getting common bases? That's what I'm going to do here. 10 to the x equals 100 is 10 squared. So if my bases are the same, my exponents must also be the same. So that would mean that this is equal to 2. I'm going to erase this and do the next problem. I'm going to set that equal to x again, just like I did the last several problems. Remember, the base is 10 because that's a common log, and 10 to the x equals 100,000. 10 to the x equals 100,000. I'm going for that common base again. 10 to the x is equal to 10 to the, well, I've got 1, 2, 3, 4, I missed a 0, 5 zeros. So that's 10 to the 5th. Bases are the same, so my exponents must also be the same. So that would mean that log base 10 of 100,000 is equal to 5. This one, again, there isn't a base, but there really is. It's 10, it's just not written. I'm going to set that equal to x, and I have 10 to the x equals 1 million. So 10 to the x equals 1 million. I'm going to go for a common base again. 10 to the x is equal to 10 to the 6th power, which means x is equal to 6. So log base 10 of 1 million is equal to 6. Here's the common log. Actually, the common log is right down here. This is your exponential function that leads to the common log. Remember, logs and exponents, those functions, those graphs are inverses. So right here, I have y equals 10 to the x. That's just an exponential growth model. I only have 3 points graphed, or plotted. I could have put more. And when I change to the logarithmic way to write that, oh, but look, I didn't write that 10 in there. That was on purpose. Remember from the problem we just did, if you have a log and there's no base, that automatically makes that base a 10 right here. So these two functions are inverses of one another. And that means that if I were to draw this line, y equals x, they're reflections of one another with respect to this line, y equals x. Also, the x's and the y's change places when I go from a function to its inverse. This was negative 1 1/10. This is 1/10 negative 1. Same thing happens for the domain and for the range. The domain for this function, and I'm going to have to start over again, so stay tuned for part 3.